Okay, guys, can you hear us? Can you write something on the chat to let me know if you can hear us? Okay, so it's my pleasure to introduce Bartolomeo Della Corte, who has been working in our lab until a few months ago. He got his PhD and he now moved on to work in Singapore at Autonomy. So he's working on autonomous cars. Although this presentation will not talk about what he's working on, probably also because there are NDAs to respect. Um, so he will talk about his PhD research and probably tell us just tiny bit about what he is doing now, but at a very high level. So take it away. Thank you very much again for accepting to present.
Thank you for the invitation. Hi all guys. As Roberto already introduced me, my name is Bartolomeo Della Corte. This is just a brief history of my academic and research stuff. I started studying computer engineering at the University of Naples, where my thesis were more related on UAV and micro aerial vehicles. Then I moved to Rome, so I was attending the same courses you're attending now during my master in artificial intelligence and robotics. I continued it with a PhD in computer engineering, advised by Professor Grisetti, where my work was mostly on mobile platforms, either in terms of calibrations of these platforms, in terms of building up representation of the environment, so with what is mostly known as simultaneous localization problem, and how to make this platform able to navigate in the environment. After I got my PhD, I moved here, where I'm now in Singapore, so I'm like 6 hours ahead of you, where I'm working as a research scientist in Roberto introduced it as Autonomy. Now it's former Autonomy, is Hyundai Aptiv joint venture, where I'm working on really challenging task about mapping for autonomous driving. And in particular, I'm one of the research scientists of the mapping team. Well, let's go with this, the presentation of today. So, as you may know, we have many applications of mobile robots today. Many of them are really close to us, either in our home places or we see them pretty often in TV. Let's say that many of us may have, for example, a vacuum cleaner robot, either for vacuum cleaning or for our gardens. And that's, of course, works because it's able to extract a model of the world, to build up a model of the world. Of course, if we buy the cheap one, it will just go around and hit the walls by bumping them. In that case, it's not building up an environment, so reconstruction is just acting and reacting to at that level. But I mean, an intelligent machine, in this case, has to be able to build up a good representation of the environment. When things get even more complex and dangerous, so in case of goods transportation or human being transportation, in that case, it's of course mandatory to have a good representation of the environment. So this is true either for vehicles on wheels, as cars or trucks. It is indeed true for aerial vehicles, and it's regardless the fact that they are, in case of ground vehicles, legged-based robot, quadruped, or whatever. One of the applications that nowadays is going really on in research is the underwater mapping, for example, and you can see here one example of robot for underwater slam. So what am I interested on? Building systems that are able to interact with the environment, and so that need this model requires some steps to be followed. First of all, we have to take our platform to calibrate them, where calibrate means know exactly what are the intrinsic parameters of the platform and what are the extrinsic parameters of the platform. The intrinsics, you may imagine, you have already studied, for example, in vision, that a camera has a camera matrix, so has some information stored about the number of rows, number of columns, the focal distances. So that kind of parameters are part of the intrinsic parameters of a platform, where with platform I intend either the robot itself and the sensor with which is equipped. Then, of course, we need to know the extrinsics of the sensors, meaning that we, of course, imagine we have a car, we want to know where a certain sensor is located on the car. And a representation of the environment is needed, I already told you, but of course several representations are possible. So you can imagine that I may represent the world made of point. I can also represent the world made of higher level features, as may be, for example, lines or planes. Just to give you an example of what is a map made of points, you can have a look at this. It's just a 3D reconstruction of the Freiburg campus. And well, you can also find it out just by, this is my website, and there is one article on map merging if you want to have this viewer. But as you can see, this is a pretty dense reconstruction where we can see all these points. Of course, storing at each time the points and their position, and I mean, when we can just have this building, for example, here represented as 4 planes, is pretty costly in memory. So this is also one thing that has to be taken in mind when doing mapping. And finally, of course, once we have this representation of the environment, another thing that we want to have is of course, the ability to move inside the environment. So the robot has to be able to compute a safe plan from a starting point to an ending point, and to actually apply the control laws to track this path. These 3 problems are known in literature as calibration, simultaneous localization and mapping. So SLAM stands for simultaneous localization and mapping, and navigation. What I'm going to present you today is a methodology that leverages least square solvers. You can imagine, if you're not familiar with state estimation or least square optimization, we are going to find a common way, a unified way to represent this problem and to solve them. And you can imagine this presentation as some kind of one least square to rule them all, let's say, to rule all this problem all. Of course, it's not even true that there are no other possibility to solve this problem in a more efficient way. One thing that as engineers and as scientists you always have to learn is that you have many instruments, many tools that you are able to use and that you learn at university. Once you learned it, you have to also learn when to apply these tools and how to apply these tools. So yes, this presentation, I will always use the least square as a tool for solving these problems. But in many cases, there are more efficient tools. Keep this in mind. Otherwise, every time you have a problem, you just have learned how to use the hammer. You will use it even for unscrew something, and it's not what you want to do. So let's first see what's the way we represent the state in our state estimation problem. And let's say that we have we consider our world made of our problem as a stationary system, where we have with X usually the non-observable state variable, while with Z we represent the measurement. Of course, you can imagine that with just with a vacuum cleaner in your robot in your house, the state you wanna estimate is just represented by the position, actually the pose of the robot. So X and Y pose, if you just imagine the robot cannot fly. So X and Y coordinate, and the heading, so the yaw angle, let me call it like that, of the robot itself. While the measurement, actually, they depend on the kind of sensor with which the robot is equipped. So in case of bumper sensor, the Z is just on/off of the bumper. In case of a camera, the Z may be either the raw image of the camera or some features extracted from the image. In case of a 2D Lidar, for example, maybe the measurement of the distances, the perceived obstacles. I mean, depending on the sensor Z, the value of Z may vary. And of course, the state is distributed according to a prior distribution, while the observation model is known. I mean, if I put a sensor on a robot, I should be able to predict what I'd like to see, so I can write down my observation model. Our goal, so, is to find the most likely distribution of the states given the measurement. Of course, we have no access of the actual position of the robot, but we have access to the measurement. So given this measurement, so given Z, we want to estimate X. It's pretty common. Our assumption is that we have a uniform prior, so everything is Gaussian in this world, and we have to define a measurement function. It is pretty important to solve these kind of problems. In case of linear measurement function, everything is pretty straightforward to solve. So we just have this linear system. Well, I just jump on the full math for gen distribution, chain rule, and conditioning. But the important thing is that we just boil out that estimating this mean in a pretty easy way. So just by solving this linear system minus h solved as a matrix with b, that is the vector, we solve this linear system where we minimize this error between the predicted and the measurement and the measured values. In case of nonlinear measurement, and of course you can imagine just by estimating the pose of the robot, we have something that contains sine and cosine, so we are really likely to have a nonlinear measurement function. In this case, we can linearize them by first-order Taylor expansion by computing the partial derivative as the Jacobian J, and you see H and B came out as still full matrix H, an Hessian matrix H, so it's a partial second-order derivative, while B is so-called in literature residual vector. The important thing here is that to get that just by computing the Jacobian, so applying the first Taylor expansion, we can get a linear system too. Of course, we also have cases of non-Euclidean spaces, and it's pretty common also this case. And here we just need to know that we can move on a manifold. I think you have already encountered in your master program, just operational manifold. The only thing that you have to get from this slide is that you have a box plus and a box minus operator that helps you with the manifold operation. So imagine just like that. And now let's came out with this methodology that we'll try to use to solve several different problems. First of all, the first thing that you have to do when we have to solve a new problem is to define, to parameterize the state space. What we have to estimate, what we have to came out with. In case of a vacuum cleaner for our home, we just need to know the pose of the robot. Once we have get that what we want is the 2D pose of the robot, well, we have to define a minimal parameterization. So instead of having a transformation matrix with the 2D rotation and X and Y position, we can just get, for example, X, Y, and theta. That's a convenient minimal representation with just 3 values. Then we have to define the box plus operator to make it more clear what it is. Just is a way to update our current state estimate, so our current transformation matrix, given this vector. So we take this vector, we compute the transformation with the values in this vector, so compute the rotation with the yaw and get the transformation from X and Y, and sum it up to the other transformation. Same thing has to be done for the measurement space, depending on the kind of sensor we have. Then we have to identify the prediction function, meaning once I have a sensor and I imagine that my robot is in this position, what I should see. That's the prediction. And of course, the error is defined as the prediction minus the measurement. And that's what we want to minimize. Given that, we can compute the Jacobian, and we have our linearized system, and we can solve it down. Gn stands for Gauss-Newton, Lm for Levenberg-Markov. Is just a couple of algorithms that can be used for solving this kind of problems. So in this presentation, we will solve several problems. We will solve calibration problem by making actively use of the information. We will go through the extensive use of chain rule in computing the Jacobian for a visual odometry problem with MPR, that stands for multi-Q photometric registration. Then we will work with higher level features over parameterizing the error function with Sasha, scene alignment with shapes. And finally, we'll see how to apply least square also in time horizon-like problem, solving an MPC problem in our work called Gnomic. So first of all, let's see what's a calibration problem. And this is actually the first thing you have to do every time you either buy or build a robot. First thing you have to do is to calibrate. That's pretty important because the outcome of the calibration highly affects all the other tasks you are solving. It will affect a lot the quality of the map you end up building. It will affect a lot the quality of the control laws you are applying, because if you don't know the actual parameters of the robot, dynamic or kinematic as they are, you are not able.
Sorry, Bartolomeo. We have a question
Sure.
which
Sure.
we should probably answer, which is how the robot can estimate the distance between itself and the objects. It uses just the parameters of the camera, or does it use the sensor or a combination of them?
Well, it actually depends a lot on the sensor, of course, because, well, in case the robot is equipped with a camera, you can, yes, extract features, for example, from the camera, but in that case, you do not have, if it's just a monocular camera, a direct distance from the object, from the obstacle you are looking at. So what you need to do is to continuously track that point in the 2D image and trying to triangulate it. So you may, for example, make use of the, for example, of the dead reckoning of the robot to help you out finding out 3D position, 2D position, whatever of that point, and that happens with camera. In case you have a Lidar, instead you just take the value, because Lidar returns you the depth of that point. This thing is also true in case you have a depth camera. You just take the depth relative to that pixel. Of course, in monocular camera is pretty more complex, the problem. You have to triangulate that point. I hope this answers your question. So moving on, we were talking about what's a calibration problem and what's the state we want to estimate in calibrating a platform. Well, let's say that our robot, for example, the one here on the right side of the slide, is equipped with a set of sensors. You can see some depth cameras on top. Then there is a 2D Lidar, bottom part of the robot. And this is part of the exteroceptive sensors. Then, of course, we have the dead reckoning on the wheels, that interoceptive sensor. What we want to estimate is the set of kinematic parameters of the robot. So how big are the wheels and how distant they are. Then we want to estimate the extrinsic parameter of the sensors. So, for example, where is the Lidar with respect to the centers of the wheel axis? Where are the cameras? And these values has to be expressed as 2D or 3D poses, depending on the sensor itself. And of course, sometimes when you build up this platform, may have some delay in the information you got. And in that case, you want to also estimate the time offset of the sensors. What we want to do in this work was actually also to actively use the information obtained of the by the estimate, meaning that sometimes in solving least square problems, you just take the information as just an output value. What we want to do is, okay, once we solve a least square problem, how can we use the information as a further input? Okay, let's just a sec, sorry. Okay. Now, depending on the, I'm not sure if I jumped a slide. Yes, okay. So the state space, as I was telling you, is just a set of kinematic parameters, wheel radius and distance of the wheels, and the extrinsics of each sensor that may be represented as poses. Then we have the time delay of the sensor. So we have this vector x that contains all the parameters that we want to know. Now, depending on the hardware available, either if we buy a robot or we build it by our own, so we have our custom platform, we have access to the encoders or not. Well, in case we have access to encoder, we can also calibrate the wheels radii depending on the of the mechanical hardware that you mounted up. You see a lot of math in this slide, don't worry about it. Just take as a message that the prediction function here is just a prediction of how the sensor should be moved. Let's say how I expect the sensor to be moved given the reckoning motion. So XS is the, if you look at the prediction function, XS is the pose of the sensor, while TR is the reconstructed dead reckoning of the platform. In case we do not have access to platform encoder, just let's say that we have a set of parameters to estimate, even though they do not represent an actual transformation or kinematic function. Well, in the state of the art, there are many approaches for calibrating platform. Couple of them pretty famous meaning they are cited a lot, are based on the of following a certain trajectory. Meaning that, for example, you take your robot, you look on, I don't know, you measure on the ground some distance, and you, given that, run your robot in this square, for example, path, and measure the reading of the odometry and compare it with the distance you have measured. Well, this may work, of course, but if you want really high level of precision, what you want to do is to get the idea that the trajectory that you follow with your robot highly affects the outcome of the calibration. So what we wanted to do is to analyze actually the information. If you remind a bit the introduction on least square, we have this H matrix that is the Hessian matrix that actually stores the information. So you can see it as an hyperellipsoid, a multidimensional, where this dimension depends on the number of parameters you are estimating. So in case of our platform with many sensors, we have, I don't know, 15 more or less parameters. And in this case, we have a 15 by 15 matrix, for example. So for convenience, instead of representing it as an hyperellipsoid, I will use this representation you see on the left, where I have the eigenvalues on the bottom part of the slide. The darkest the value, the higher the value of the eigenvalue itself, while the eigenvectors should be read as columns, are the direction of this hyperellipsoid. So you can see that, for example, if I just take a straight motion, and it's the case on the left, the higher eigenvalue, that is the one on the left, is the one linked to an eigenvector that points just in the direction of KL and KR, where KL and KR are two values that regulates the sides of the robot wheels. So practically, what does it mean? That just if we go straight, the only thing that we are able to estimate is the size of the wheels. We have no information at all about where a sensor is positioned on our robot. While by performing pure rotation motion, we have more or less more information, but not a completely coverage of all the cases. This is just an analysis that is meant to give you an idea on how much is important to follow up predefined trajectory or not when calibrating. So our idea was, well, instead of having a user moving the robot and maybe exciting one parameters with respect to the other and not being able to actually calibrate all the parameters, let's do the robot calibrate itself. Let's do something that is an autonomous calibration. Based on what we wanted to have is to increase this value, this phi value. Why? Because we will have at the same time either the determinant of the hyperellipsoid, that it's meant to be its volume in 3D, the bigger possible, meaning more information. But of course, we also want to have a more balanced hyperellipsoid, the closest possible to a sphere, so something that is isotropic. How is computed by this eta factor? That is just the ratio between the minimum and the maximum eigenvalue. So we use this measure to say, hey, robot, just calibrate yourself. How is the procedure? It's just an exploration-exploitation approach. First of all, the platform executes a set of motions, so standard motions, for example, go straight, or just rotate in place, or perform some sort of arc motion, and store the outcome of the H matrix. Once you've done that, the platform is able to exploit the knowledge by selecting a sequence of motion that aims to maximize the information. So just by going at the results, for example, during the exploration phase, we just go forward and we store the information we got. So we just got information about the encoders. Then we do some sort of arc motion that gives more or less good estimate on all the parameters. And then we do rotate motion in place that it's really good to estimate the expose, for example, exposition, x coordinate of the sensor. Once this is done, an example of typical run of our platform is it starts with the most prominent motion, that is the straight, for example. Then he try to fix the baseline by rotating on the spot. And up to then, it starts a refinement session. So what we got is just a procedure in which the robot, depending on the parameter that we asked, is looking for the most prominent H matrix given the motion stored in the database. So the results of this study was, well, in case of unsupervised calibration, our robot is able to perform better in terms of pure dead reckoning, as you can see. The ground truth here is measured by 2D mapping with the Lidar, while the other trajectories, the green and the blue one, are obtained just by dead reckoning. The blue one with standard supervised calibration, so following the square path, while the green one is obtained with our approach of unsupervised calibration. And just to give you another example how effective this is just an example of 200 and more meters of trajectory at the department, at the first floor of the department. As you can see, just by there is an error close to the 0 coordinate, so at the beginning of the trajectory, but as you can see, the rest of the shape of the trajectory is pretty close to the original. Of course, you are not expecting from a dead reckoning system to be accurate. That is meant to be a measure of prediction for the motion and a really good prior for mapping, but not more than that. So these results are really good in terms of dead reckoning. And this is the 3D map reconstructed just by using dead reckoning again. So once you have done with the calibration, so once you have your extrinsic parameter of the platform calibrated, you can start to map the environment. So you may have different sensors. You may have RGBD camera, you may have 3D LiDAR, 2D LiDAR, wherever. One of the most prominent approaches for strategy for registering point cloud, so to build up actual map, is the iterative closest point algorithm, known as ICP. ICP is well known to work either with monocular camera by extracting features, or depth cameras, or 2D or 3D LiDARs. Depends on the application you want to have. And how it works, you can see here on the monkey GIF on the bottom of the slide, courtesy by you can find it out on the PCL library, where the 2-point clouds, even though they are disaligned at the beginning, are then aligned. So one of the most prominent approach, even though there are tons of approaches going out in literature in the last 20 years, even more, was dense visual odometry. And we were really interested.
They're asking how useful is sensor fusion in this kind of applications?
In this kind of application, you mean mapping or calibration?
I think they refer to the calibration. I'm not sure exactly, but I cannot say the name. If the student can confirm.
Well, let's say that I'll try to answer for both. Yeah.
Yeah. Okay. Yes.
Okay. Sensor fusion in calibration is pretty important, and of course you can refer, for example, to this. If the set of sensor, we are doing what is called motion-based calibration. So we are comparing trajectories obtained by running visual odometries on camera, or running scan matching on LiDAR with the dead reckoning, and based on that we can establish the transform of the relative pose. Of course, LiDAR is usually more precise than the visual odometry that can be obtained with a camera. So in that case, by fusing the information, meaning that by putting in the same optimization both the information of the camera and the information of the LiDAR, so have them linked in a way that the two poses are linked by each other. Of course, we imagine that camera and LiDAR are not moved one respect to the other. Having a more precise estimate, the one from the LiDAR, helps also during the optimization the estimate of the pose of the camera. So in this sense, having fused information, meaning that we use both in the optimization, helps a lot in terms of accuracy. For the other part of the question, having registration problem, visual odometer or mapping problem with multiple sensor helps when it comes down to specific cases when some sensor cannot work. For example, having either a LiDAR and a camera on your robot helps, for example, in case your camera moves from your robot moves from a room where there is a lot of light to a room where there is no light at all. So, for example, you are not able anymore to track your features because there is, lighting changes is really affect a lot the visual odometry and mapping with cameras. So in that case, LiDAR helps. In case you have, depending on the kind of LiDAR application, fog or this kind of phenomena, well, you may found advantages in using radar, for example. So combining them, having fused sensor, fused information from many sensor always helps. And I mean, that's an answer that is true either for calibration and for mapping. Of course, too many information fused together, you have to be good in balance them, meaning that you will end up with a single optimization where each one of these sensor has his own weight, and you have to weight them based on the confidence you have on that sensor. I would trust more on a LiDAR than a camera, for example, but depends actually on the application. Okay, so sure.
So yeah, we have another question, which is, what is the application of the 3D LiDAR sensor that you have mentioned on the slide?
I assume the one that I have now showing out. So, well, what is the application of 3D LiDAR? That's pretty, I mean, these ones, for example, this map here is built up with a 2D LiDAR that was tilted, meaning that you see each one of these pose here, each one of these hole here was the actual pose of the robot. So here everything was working in a stop and go fashion, meaning that the robot was in one of these positions, for example, and the 2D LiDAR was rotated on place to get a 3D point cloud. Then the robot moved, and this was repeated again. Of course, you cannot have something like that working for a car or for whatever other application you can imagine. So having a 3D sensor, I mean, that gives you directly the 3D without the need to stop and register is, of course, a pretty useful condition. So application may vary a lot from autonomous driving to well, whatever you can imagine. Even indoor mapping may be helped a lot with a 3D sensor. Just to show you, for example, an outcome of a 3D LiDAR on street. This one is, for example, you can see there is a direct reconstruction of the trajectory with a 3D LiDAR. But I'll arrive on that in a couple of minutes. Okay, so as I was saying, one of the most famous work by the TUM University of München was DVO. Why? Because it has worked with RGBD cameras, was pretty fast, meaning that it was able to process the images at more than 30 FPS, so the actual frequency of the camera, and was a frame-to-frame approach, meaning that the motion of the camera was computed one frame with respect to the other without building up a map. But the problem is that this approach was pretty sensor specific, meaning that many of the tricks in the code, because there are many tricks in the whole code, you will find open source with respect to what's written in the article, is the fact that here were used, for example, Taki weights, normal OT distribution, depending on the specific sensor. What you wanted to do is to have something that was more flexible and was able to work with different sensors. How we did it? By exploiting the so-called photometric error function. What's just a photometric error function? You can see it by it's the difference between two images. One is computed by projecting a 3D model to the image, and the other is just the image obtained from your camera. The solution we ended up with was I'll just show you the schema here. Was a pretty flexible solution where we had the 3D model top left that is projected. So depending on the projection function, we can have different models projected. While this was processed to obtain J hat, and this was and the error was computed with respect to the current image, the one that comes in on the bottom right of the slide. So you can imagine that if we change sensor, so if we move from RGBD camera to a 3D LiDAR, we just have to change the projection function. So instead of having a pinhole projection, as you've learned in vision and perception course, we will have a spherical projection for a LiDAR, for example, given the intrinsics of the lidar. So by changing that, by changing the relative Jacobian block of the projection, we can just switch sensor. So our approach would work either with RGBD camera here. This is, for example, a live reconstruction from a camera. You see how dense is the reconstruction. Work with sparse 3D LiDAR. For example, here is a reconstruction of the catacombs of Naples. And worked the video I was showing before with a full 3D LiDAR, the one that is used, usually put on cars, for example. This one is from the Velodyne. There are many companies out there nowadays that produce this sensor. And you see how well are the clouds aligned and how fast is the trajectory compute. This is from the Kitty dataset, pretty well known in the SLAM community dataset for benchmarking SLAM approaches. Okay, as I was mentioning you before, there's still a problem here. The fact that we have too many points and we are storing in memory a lot of points. While, I mean, a street is made of planes, as you can imagine it. Or, for example, a semaphore, a line sight, is made by some sort of polygon that is on top of a line. So what if we try to reduce the footprint of memory by moving to higher level primitives? So instead of having points, let's say that we have some reconstruction as the one you see on the bottom. So planes and lines, or other than points. How, does it help or not? And how does it change in terms of computing error function and solving our least square problem? Well, let's say that we can end up calling these features, so point, line, and planes, as matchables. And we can see that, of course, there is something in common between them. If you remind a bit what is a quadric, you can see how all these primitives can be represented as degenerate quadrics. So, for example, a point can be seen as a sphere with no radius. A line can be seen with a cylinder without radius. A plane can be seen as two planes with null distance. So, three kinds of quadrics degenerate to this matchable representation. So, by just representing a matchable in terms of centroid, so the point P, direction, so how is the shape oriented in space, the rotation, and an activation matrix, lambda, we can end up just by not changing at all our algorithm, just by moving just by changing the representation of the features. So with this activation matrix, of course, we just change the components we want to work on or not. You see, for example, how we evaluate the formula on top, the distance between two lines, a plane and a line, or a line and a plane, for example. Of course, if you want to compute just the distance between 2 points, there is no need that you know how these points are rotated in space. I mean, they are just 2 points. While if you want to compute the distance between a point and a line, you have to know how the line is oriented in space. That's why we have this activation matrix, to activate and deactivate those components. So to do some experiments, first of all, we had to extract points, lines, and planes from our images. We were using RGBD cameras here. Points and lines are just extracted by standard OpenCV functions, along with their descriptors. While to extract planes, we did something a bit more tricky. We took the curvature image, how it's computed. Once you have the depth, the image A, you compute the normal from that image just by seeing how the depth changes. From the normal, you get the curvature. So, and you do the negative of the curvature, and you get the image C. And from that, you decide by clustering in which area you want to look for planes. So you cluster, for example, these 3 big walls, and you check the eigenvalue, the SVD decomposition of the set of points. If there is not so much, if the dominant direction is just, if there are two dominant directions, it means that the other one is just not present, meaning that here you have just a plane, while if you have another direction, you will have something that is more curved. So you will have, I don't know, pillows, this kind of stuff, and you discard that components. So just by this simple pipeline, so we extract data, we extract our features, we associate them with KD3 if you want to know it, and by registering them, we ended up with this simple pipeline using higher level features.
Bart, can you hear me?
Sure.
Yeah, okay, so we have another question, which is, by any chance, is there any magnetometer offset or error in getting the orientation?
Well, I want to say that it's pretty specific, the question. I want to, let me say, for calibration, if you, well, in calibration, for example, the presence of magnetometer or even inertial measurement unit, in that specific case, won't be very helpful. Meaning that for motion-based calibration, so by comparing trajectory, we would have to integrate measurement. And from the IMU, integration for more than short measure of space is not so high quality in terms of trajectory, of the outcome trajectory. For magnetometer in the orientation, yeah, that would be well, of course, better. We did not have the chance to test it, but I want to guess that in many real application, mostly on, I think I've read a couple of papers in bathymetric SLAM, so underwater SLAM. They were used a lot, so for orientation. But I'm not so. I have not enough experience in that kind of sensor to completely answer your question. Thank you. So this is just a set of results we obtained with our approaches, just by proving that the full use of high-level features improve the robustness. For you, these are just numbers. I'll show you the full reconstruction of the software we ended up with. You see there are not so many points. There are these planes that helps a lot in the in keeping track of the environment. So let's say that we just three features, practically these three big planes that the camera was seeing a moment ago. We were able to actually have a robust track. And that was, I mean, pretty nice. You can imagine, for example, having such a representation in higher spaces. So if we have the problem of scalability in keeping in memory too many points, when mapping, for example, a city, we can move to something that is higher level to get something better. But of course, there is a counterpart in the problem. Imagine that you have just two buildings, one after the other, that are, I mean, associated by your association that works with the distances between two planes. In that case, you will end up matching two planes that are not aligned, actually are the phase of two buildings. I mean, there are some not trivial things to be handled once you move to this kind of higher level representation. But of course, this is one direction where the SLAM researchers are going through to reduce the footprint memory and having something more robust than just points. We did also other experiments in adding loop closure to the system, meaning that we get the idea on when we were crossing again the same region. Here are just some results that do not mean too much for you, but for us, very important to get the idea on how much was improved the results by adding loop closures. So once you have our representation, either if it's point-based or plain line point-based, we have our robot that is perfectly calibrated. We want to move our robot, so we want to have something that actually goes. As you can see, one of the most prominent approaches is nowadays to fast replan trajectory, to handle dynamic object, to do a lot of fancy stuff. As you can see in the video, is working with MPC technique, model predictive control. And we also put our hands on this. And of course, we faced the two big problems that you have. Of course, it's really cool to add constraints to a model predictive control problem. It's pretty easy to do. You just add constraints as stay away from obstacles, or I want you to be faster or slower, to be smoother in your trajectory. But of course, you have some sort of problem dimensionality that has to be handled. We try to handle that by moving from standard representation to flat output. And after that, we also try to take advantage of the theory behind MPC for having something that was more precise in the first part of the trajectory and more coarse at the end. I will explain it better. First of all, our dimensionality reduction was done by using flat output. I assume you are familiar with that, at least from the autonomous and mobile course, autonomous and mobile robotics course. And our state here is composed by all the poses of the trajectory and the input to get to that poses. What we wanted to do actually was to improve the quality of the trajectory, but without losing too much in terms of real-time ability to solve the problem. So what we did was like, okay, the theory of MPC says that what you should do is to compute the trajectory and the input, take the first input and pose, take the first pose, compute the input to arrive to that pose, discard the rest, and recompute it. Of course, you can cache the value, you can do all the optimization you want to do, but that's the theory of MPC, what you should do. Compute everything, take the first step, recompute everything. So our idea was, what if we, instead of having something that is a uniform trajectory, we have something that is more dense in the beginning of the trajectory and more sparse or coarse at the end. So what we did was like, we have the full problem. We scale it down just considering the first step of the solution. Then we compute a discretization error by having an higher order approximation and say, okay, I assume that, for example, the error may be too high. Here in the second step, for example, of the solution, I have an error that is too high. Let's insert another step here by just interpolating, and let's optimize just this scaled problem. Once we have optimized that, what we obtain is something that is, as you can see, we have more steps at the beginning and less at the end. This proved to be very effective in terms of real-time capability, because the solution of the problem you are obtaining is from a scaled problem, meaning that the problem is not so big, so you have not so many real-time issues, while you are still having a pretty smooth trajectory at the beginning and coarse at the end. And this works if your solver itself is called constantly. So you are actually just keeping the first step and discarding the rest. We tested it with the rotor simulator by ETH. It's public, free, works with Ross and Gazebo. If you are working with MPC, I advise you to test it here. It was also used in the Europe challenge, an European challenge for robotics, couple 6 years ago. And well, we tested it either for pose regulation and trajectory tracking. For pose regulation, we ended up having something that was real time, still real time, and was working even with really few steps, having our lattice more dense at the beginning of the trajectory. And this is instead the experiments of trajectory tracking, where we were following Bernoulli-Lemniscate trajectory in 3D. So it's like an 8 shape, but in 3D. And as you can see, we have slight advantages in applying the time mesh refinement. That is the approach on the bottom with respect to the one on top, that is standard MPC approach. So what we have done in this presentation is a journey from having a platform, either custom or built, calibrate this platform, trying to use the information to let the platform to calibrate itself. We exploited the chain rule for having in MPR, in multi-Q photometric registration, an approach that was able, just by switching the projection function, to work seamlessly for 3D LiDAR or depth cameras. We over-parameterized the error function. If you remind, we were using the same error function for point, plane, and lines by meaning of the degenerate quadrics, sorry. And we applied also the least square to time horizon problem. As I told you, is not the best thing to do to just keep an approach and use it in every single problem you face. These are, of course, some experiments. For example, in MPC, there are tons of literature about dynamic programming and other techniques to be that are way more effective in solving MPC problems. But I mean, this was a presentation to give an idea on how a tool can be used in so many different problems. This is the set of publications that accompany the work I've presented you, and mostly my whole PhD. And well, waiting for your questions. Thank you all for attending this seminar, and thanks again to Roberto for inviting me.
Thank you for giving this presentation to us. And yes, so let's wait for some questions on the chat. So yes, we have one immediately. Hopefully others will come. So the first question is, I didn't get in which sense the dead reckoning calibration is automatized. In particular, where should I use the phi function, which is the function of the eigenvalues in the least square machinery?
Okay. Okay. Let's say that. Okay, this is the slide. Yes. Okay, just to get the question, I will rephrase it. You didn't get how, well, in which sense the procedure is automatized, and where you should use the phi function. Okay, the phi value actually. So it's automatized in the sense that actually the robot will start moving itself. How? First of all, you have this exploration phase. So your robot is moving, you are collecting data, and you are solving a least square problem here. By solving this least square problem, you collect a set of H matrices, where H is Hj in this formula, for example. So for each kind of motion, you will have one H computed in your database. Once you've done that, you get this information in terms of the SCM matrix, and up to now you forget a bit about the least square and say, I want to maximize this H. Which path should I take? Which motion should I take next to maximize this H? And you will check it just by summing up your current H. So at the beginning will be just an empty, a zero matrix, and the the one that has the phi value higher. So for example, the straight motion, let's say. So first of all, you will do just straight motion. After that, you will select the second one based on if I sum up what I am expecting to have from a rotation motion, should I get something better or worse? If I sum up something coming from a straight motion, should I be better or worse? So this is done for collecting data. Once you have finished collecting this data, you run the full least square calibration. So the phi itself is not used inside the least square machinery, it's used to select the motion that gathers data for the least square machinery. And I think this answers both the question. Either is how is automatized, so the robot will select the motion and gather data by itself, and the least square machinery arrives at the end of the gathering motion. So once the robot find out that no other H matrix is improving my current H matrix.
Okay, yes, thank you. So we have a couple of other questions, which is, sure. So the first one, so just to answer, we have a question which is, can I ask a hardware question? I think yes, and I mean, Bartolomeo will respond. I mean, as much as he can, but
sure.
Yeah. Then another question that we have is, I haven't understood very well the utility of over parameterizing the error function.
Okay, I'm already at the good slide. So yes, you may wonder why we wanted to have an over parameterized error function instead of having 3 different error functions. Let's say that yes, we can have just 3 different error functions, one for points, one for lines, and one for planes. But there are 2 advantages in having this over parameterization. First of all, let me call it elegance in your coding, meaning that once you have converted your features in a matchable, either a point or a line or a plane, and you have expressed it as a degenerate quadric, from that point on in your code, everything works regardless of the feature itself. Meaning that also the data association is working by associating points with planes without knowing that that's a point and that's a plane, just by using the activation matrix inside, by computing this same error function as a nearest neighbor distance. So this avoids a lot of context switch in your code, mostly in the data association. And from the other side, it's way more, let me call it elegant in terms of either coding and I mean, coming out with a unified representation. So it has, of course, these 2 advantages.
Okay, so we have other questions. Good. One is it fine to do the calibration phase only once, or is it better to refine the parameters each time the robot is started?
Well, that's a good question. I can answer by experience. We were not used to calibrate a lot robots in the lab, meaning that we were calibrating it once, mounting the sensor on top of it, just calibrating, and that's it, and storing this txt file with the calibration as a holy file in our system. But of course, after a while you were using, there were many students passing by, or the same robot was used by for several different experiments, and you will end up just touching the sensor. Maybe we had also a robot with inflatable wheels, for example. With time, that wheels were not inflated the same anymore, so the wheel radius even slightly changed. So depending on I want to say, as a rule of thumb, every time you turn on your robot, you should have a fast way to calibrate it. it will improve a lot your performance. If it's an industrial robot, so if you have like serious joints, something that is, I mean, thought to be durable, well, of course, you, for experience, you won't do it every single day, but once a month at least you have to recalibrate your robot, even if it's an industrial one. With a custom one, do it every day. That's the only thing that may work if you actually use it. If you just turn it on and then turn it off, well, nothing will change.
Okay, thank you again. We have other questions. So, are there other methods of interpolation when the discretization error is too high besides the cubic method?
Besides cubic Hermit?
Yeah, cubic Hermit method.
Well, I mean, it actually depends on the kind of, on the way you have parameterized your state, because you are actually interpolating states. So if your states are just poses, you can just apply a standard slurp interpolation for rotation and like linear interpolation for translation. While our state, I mean, we were pretty forced to use cubic Hermit for flat outputs. So I have no idea if there are other methods. It's more, I don't know if it's control related question or not, but I have no aware of other method to do that. Sorry.
Okay, so we have the other question now, which is, suppose that we have a robot and in general we have three jobs: the movement part, the image processing part, and the sound processing part. So how many processors do we need? With just one processor, can we implement everything that we need? And this is not specific to Bartolomeo's expertise, but I think, I mean, yeah.
It's pretty general.
Yeah.
Let's say that I can give you an example of one European project we were working at university years ago. That is the Rovina project, for example. Let's say that in that project we had one 3D Lidar, 3 cameras, 3 different depth cameras. Then we had the robot that was moving. And inside the robot there were 2 laptops. I mean, was a lot of processing. That's why the 2 laptops. But the most important thing was the not the data processing, while the data transmission. Say that you have your camera. I don't know. It's just a standard cameras, for example, a standard depth camera. So you have one single laptop. You attach your USB to your USB to the camera. If you attach another USB and then another, you may end up losing information. That always happens, meaning that instead of having a 30 FPS camera, you will end up having 30 FPS, but each 10th frame you will lose a couple of frames. And it's something that you do not want, of course. So what we did in that project, what I arrived at the end actually, who was there before me did it, was to use one microprocessor for each sensor, meaning that each one of the sensors was attached to one single. The actual hardware was the Banana PI, but by the way, you can imagine, for example, one Raspberry for each sensor, and then one gigabit Ethernet to connect everything and to stream data in Ethernet. That was the only way we ended up not losing data, because the amount of data coming from the sensor was really high. If your question is related to processing the stuff, either you may have, if it's a small processing, for example, you are just extracting features from image, fine, you can do it on your Raspberry and then process the features and then, transmit the features to the laptop. But I don't think that's the case. Otherwise, you won't have this kind of problem. If you're running heavy processing on the image, well, if you are actually losing data, yes, maybe you will end up having separate, you called it, I think, jobs. I want to say even not small laptop, but small microprocessor. But first of all, check your, I mean, it should be really an expensive computation. Check your algorithm for what's doing first. I don't know if it answered the question. I hope so.
Yeah, I think this is a pretty concrete answer to that question. The student also thanks for the answer. We have one more question, which is a quick question about sensors. What are the pros and cons of lidars versus...
Sorry, what are the?
Pros and cons of lidars versus active sonars.
Sonars.
Yeah.
Well, pros and cons of using lidars against active sonar. I have to say I have no experience with sonar. I mean, seen a couple of data sets. I've seen. I went through some data sets. It depends on the application. For example, I don't know, underwater, you will never use a lidar. You will use a sonar. In terms of indoor, for example, with a small robot, sonar may work. You may need, it depends on the sonar itself. I mean, I experienced it with sonar, but was seriously not easy to handle it because the noise coming from sonar data is really high. And the frequency, but we were using really cheap solution. We were looking for cheap solution in sonar, and the kind of measurement we got were really noisy. So we were able, for example, to perform localization indoor with just sonar from a map built by Lidar. But I mean, Lidar was way more reliable. I mean, there's a highly difference in terms of cost. Lidar will cost way more than a sonar. But in terms of high level sonar, I've actually never used them. I used super cheap one, and it was tough, I have to say. Everything worked, it was super cheap, but it was really tough.
Okay. So I think we don't have any other questions. So if that's the case, guys, we're done for today. There will be no class next Tuesday. So we'll be back on the 21st. So I don't want to set your expectations high, but we should have a person from JPL NASA giving us a talk. Unless something goes wrong. You know, these times are weird, so it could be. If not, we'll see. So have a good day, have a good Easter, and go back to whatever you were doing. Thank you very much again. Bye.
Thank you. Stay safe, guys.
Okay.